Our speaker is Professor Joydeep Chakraborty from IIT Kanpur, and he is going to talk about effective field theory, why and how.
Okay, so thank you, Subrata, for organizing such a school for these grad students, and thank you, Jose, for coming down from this long distance to teach us about this thing. So my role in this one lecture is very much supporting. So what I plan to give you a sense of what is effective field theory, which already Jose has introduced to you, and then how you should use that. So rather than going into detail in one of the specific, construction, I will try to give you a glimpse of those ideas and try to motivate you that why this is the right time to do the effective field theory. So let's see. So the interesting part of physics is basically, as you know, the physics of different length scales are actually different. So if you have heard about the word like the theory of everything, that doesn't make any sense in real scientific community, because at different length scales we have a different kind of physics phenomena. So now if you look into very natural unit point of view, so you can connect this energy, mass, and this length and time. So everything we can recast in terms of the energy, and that's what the one scale when I'm talking about repeatedly. I have not mentioned the mass scale or whatever, but uniformly that I'll be using the mass scale for that. And now if you look at the experimental searches and versus the theoretical proposals, so that actually encompasses the directionality of the scales. For example, when you construct a theory model builder, right? So what you try to do, you try to use the symmetry and all those information about the quantum fields and so on. You try to write a Lagrangian on that thing, and you try to predict something which you expect to be discovered in the future. That means basically in the much more higher energy scale. And experiment actually try to dig out those energy scales. So it's like a complementary behavior from their side. And if you look into already our known range of scales, so if you see around the mass scale of muon and the I guess this electron, and that's basically the low energy theory we talk about. And there one of the interesting phenomena is basically that actually opens up the notion of the effective field theory is the fourth Fermi theory of muon decay, and I'll come back to this example. And then if you go a little bit more higher energy side, then you find out the standard model where you have a different kind of hierarchical masses. So you're starting from top mass to W mass, and all those scales are there. And this much information we have already explored in our experiments, but we have different kind of ideas that this can be the complete way of looking the nature looks into this low energy or different kind small length scale physics. So maybe something more is waiting for us, and that's what we call the beyond standard model. And actually, unfortunately, so far we do not have any definite clue about the beyond standard model. So the idea or the game is to basically boils into the fact to understand or maybe find out a good mechanism to understand or pin down what is the beyond standard model. It's a model building way of doing that, or effective field theory can play a very important role to do that thing. So you can see that I was talking about the theoretical proposals, and the phenomenological explorations are actually giving you the complementary notion. For example, you start with a low energy theory, right? And then based on the symmetries and the quantum fields and informations, what you do in a bottom-up approach. So when in the bottom-up approach, basically from the low energy theory information you use, and you try to construct a theory at the high energy. And here you are actually have no clue what could be the unique theory. So better you rely on what are the informations that you have, and you use that to predict kind of a high energy theory. This is a bottom-up approach. And another way to look into that, okay, so you start with your favorite theory, which you define as a UV theory or some high energy theory, and then you know what is not part of the standard model on that UV theory, okay? And then if that mass scales, as Jose was talking about, decoupling and all those things, then the decoupling limit, certainly away from the electric scale, then you can integrate that out, and then you basically construct a low energy theory there. But these two are actually complementary, and they are connected by an interesting bridge, which I am calling unfolding. What is that? For example, it can be the other way around also. For example, from the experimental point of view, experiments doing different kind of fittings of effective operators and so on, all those things. And then you basically know, okay, along these effective operators, there are some X's on those things. Now the next question will be, because that is our primary hunch for that, what is the theory that can explain that data? So instead of having a blind hunch, what we can do actually, we can have a symmetry driven way, we can unfold those effective operators and try to see what are the minimal way to extend the standard model to such that we can explain that data. So these are the three important things which actually develop in I would say modern aspect in the last 10-15 years. So now coming back to the again slightly repetitions what was already told, what is the effective field theory. So this is like a technique, of course, it's like a quantum field theory technique that smells the presence of some unknown physics if it is there in the corner without much knowing or unfolding about that aspect, right? And we have already seen there are two distinct and complementary approaches, which is like a bottom up from the low energy theory to high energy theory, guessing about that thing. And if you start with some important or interesting phenomenologically relevant some UV models, you just integrate that out and then come back at a low energy in terms of effective theory. So these are two complementary approaches. Now bottom up approach is basically introduced in a much more primary way of the effective field theory, because that is actually the essence, it contains actual essence of the effective field theory, because that is what it was built for. That if you do not have any clue about the UV theory, but I have a low energy theory and the information, what I can say maximum about the UV theory. But then there's a complementary behavior top down. So though it's called the effective approach, but if you think carefully, this is actually the effective way of doing the full theory calculations. Okay, so you can do the full UV theory calculations, okay, and then you can have your predictions of all those things, but we can do integrate out if the UV scale is away from the low energy scale, and then we can reduce the UV Lagrangian into an effective Lagrangian. So it's like an effective way of doing understanding, and why that will be useful, it will be clear when I talk about those things more. And we will learn to blend these two methods to suitably solve our big question. Okay. And these are some useful references for effective field theory. Okay. So now this is the big question. So we have predicted actually 1,000 and thousands of UV models. Okay. So every day we come up in archive some new models. Either we change the interactions, we change the quantum number of the fields, and we write a new Lagrangian. Okay. So in since the promise of the LSC, we have built possibly more than 50,000 models. Now the question is really, what does the nature going to follow? Okay. So then even if we find out some kind of excess, okay, the next question would be, how do we discriminate among those 50,000 models? Okay. So that's why the kind of question that we want to understand, that there's an inverse problem. If you have some kind of excess, okay, now what is the best way we can translate, if not pinpointing the exact theory, but what kind of mu physics can encompass that excess? Can you talk about something, and can you use effective field theory as a weapon to do that thing? That's the big question. So that is the cartoon actually telling you that thing. So basically what you do, you have a low energy theory, which in our case is the standard model here, and then using that information, we try to construct the effective operators of different dimensions, and because they are basically suppressed by higher scale, so I can partially truncate them. For example, dimension 6, dimension 7, dimension 8, and so on. Okay, and this is the big pond you can see. This is actually complete set of operators. Okay, and then what you do, you start with different kind of UV theories, and these are, let's say, this capital phi are basically non-standard model particles, and these are heavy because our search in the LSC actually signifying that the new physics scale is basically away from the electric scale. Okay, so that's enough motivation for us to say that these particles are possibly far away from the electric scale, and we will integrate them out. And once we integrate them out, so whole this UV theory actually land up here. So the interesting part is basically the big pond that you have constructed, whatever be your UV theory, as long as it actually, after integrating out, if it respects the symmetry of the standard model and it contains only the standard model degrees of freedom of the particles, the number of operators of any dimension cannot exceed this one. Okay, this can be proved actually field theoretically and mathematically. Okay, so then you basically get these islands, right? So now you take a different theory. Okay, you do the same job, you just leave standard model degrees of freedom untouched, such that at the low energy all the operators are basically constructed out of the standard model symmetry and the standard model fields. Okay, so now you do the same job and you get a different island. Okay, and now what you see, you continue doing that thing, and what you'll find out, okay, you start with the minimal extensions of the standard model. You extend the standard model by minimally by, let's say, one particle, either as a scalar of different quantum numbers, or as a fermion of a different quantum number, or a heavy gauge boson of different quantum number. Okay, but once you integrate those non-standard model degrees of freedom, Okay, all the theories to start with were like apple and oranges. You cannot compare them, right? Because let's say standard model extended by a heavy scalar, the 2HDM, 2HDR model, okay, or you have a standard model extended by a vector like fermion. I mean, there is no way you can compare them, okay, because the parameter spaces are different, their interactions are different. But this thing allowing you to now give a platform where you can really compare them, because you have reduced both the theories on a platform where it described by the same degrees of freedom, by the same symmetry, right? So now this apple and orange are reduced into some effective apples in both the context. Now you can compare them. So that's the better handle to that thing. So, but on top of that, there's another one is basically tracing back the UV scenarios. So it may happen that from the experimental point of view, even knowing any particular theory, you may come up with some, let's say there's a effective operators O1 and O2. And now you get some excess. For example, a few years back, there's some excess in the atlas about the CP violations. Okay, exactly dimension 6 level, these operators actually can explain the CP violations. So you have O1, O2, and O3. Okay, and now what you do, we are saying that in a symmetry driven way, you unfold the operator and to find out how minimally you can extend the standard model such that once you integrate out those heavy modes, you get the O1, O2, O3. So this is instead of having a blind hunch, that's a symmetry driven way to understand that there is the excess in the effective operators, and that can be explained by these minimal extensions of this, not a single theory, but at least 1, 2, 3 theories. Okay, so you can make such a list of those kind of theories based on this technique. Okay, so now these 3 pillars that I talked about, that can be nicely understood in terms of very simple, which you know as the 4 Fermi theory. Let's try to revisit that part. For example, if you introduce the muon decay to the 4 Fermi operator, and the constant basically GF, which is of course lambda to the power minus 2 as the mass dimension, and then once you introduce this thing, then Jose already mentioned about the unitarity and the violation of the unitarity. So you can see the cross section actually increases with the energy, and that's a clear violation of the unitarity actually. Okay, so that's what it means basically, that the energy scale where you are computing, that's actually interfering with some kind of new physics. Okay, so it's not about the fault of the theory. This theory is actually effective theory. So this has some kind of limits. Okay, you can't use effective field theory arbitrarily for the large energy scale. But what you have introduced the effective theory, but you do not know where exactly effective field theory should be stopped. So whenever there's a failure of the effective field theory description, that's also, I would say, a good hint for the new physics actually. So that's what we come up with the idea of the intermediate vector boson and so on. So that's now the bottom up approach, because you have these degrees of freedom. Okay, you construct a 4 Fermi operator, which is this one, and that's the bottom up construction, because you have low energy theory, you have symmetry, and you construct this 4 Fermi operator, right? And now, if you look at from the standard model point of view, now you can perform the same process using an intermediate heavy vector boson, which is a W, right? It's a massive one. You have the propagator, you expand the propagator, which already Jose has mentioned, and now, and that's what when I'm performing the expansion of the propagator, it's actually nothing but the integrating out. It's the actual T-level integrating out. So whatever you are doing actually, you have a propagator in the denominator, which is actually non-local term, and now when you're expanding this propagator with a momentum transfer through the propagator is much less than the mass of the propagator, actually you are writing all these non-local terms, the infinite sum of the local operators. Okay, and you are truncating, believing that the momentum transfer is such that up to some k square by mw square to the power n, for n is 5, 10, depending on the value of the k, you are truncating. Your truncation is allowed. Okay, and that's what the integrating out. So now we have understood the same phenomena, and we are getting the same operator here. But now we can see that we understand the same bottom up approach and top down. And the other way, even if you do not know the standard model, for example, if you start with this thing, now what is the unfolding tells you? You basically know the quantum number of these states. Okay, now you basically try to find out, okay, what is the minimal extension of the gauge boson, what is the gauge quantum number you have. Then you find out, if you use the SU3 cross E1 quantum number of these fermions, then automatically you will find out the spin 1 object and what is the quantum number, how it should transform to the SU2 adjoint and so on. So you basically know that if there has to be some gauge boson, okay, there has to be a massive spin 1 object. Okay, and that's what the the unfolding implies. Those 3 topics that I mentioned is actually well understood through this simple 4 effective fermion theory. Okay, so now, effective field theory is a very old tool, but the way we are now trying to understand the effective field theory, and we try to use and making it very relevant and try to construct something, it's like a going on a war. So you better have a good weapons in your arsenal, and that's what we call the EFT arsenal. Okay, so these are the three things you must have if you want to make some good contribution in the effective field theory, and you use that. So these are the theoretical advancement in the effective field theory. Second is that use them because you have to classify more and more UV models. So you need better define an algorithm, and you develop your own open source programs and use them, and in collaboration with the experimentalist, you perform the fitting and all those things. So these are three pillars of the modern effective field theory. And these are some useful references in those directions. So I am just skipping them because there are some open source programs also there we have developed recently, but I am not going to talk about them in detail. Okay. So now let's focus on the bottom up approach because it's the important one, and it actually contains the basic essence of the effective field theory. So here when I am talking about the construction of the Lagrangian, the invariant, so I will name it as like invariant polynomial, because that's what it does actually, right? Because you have some symmetry and the you have the quantum fields, and when you write Lagrangian, what you write down? You write down operators which actually are invariant under the symmetry. And as also mentioned that if you have more than one symmetry, that operator must be singlet or invariant under individual symmetry. That one has to be careful. But game is slightly more complicated than that. So these are the rules of the game. You treat the quantum fields are basically nothing but the equivalence of the particles, okay, the symmetry, and you basically look for the representation theory of the quantum fields, and the quantum numbers are nothing but from the outcome of the what is the representations of the fields. And in my language, the Lagrangian is nothing but a collection of the singlet or invariant operators, okay. And as I mentioned, singlet are basically which doesn't transform under the symmetry. And what are the symmetries we should be careful about? Compact internal symmetries, for example, starting from U1, SU2, SU3, okay, it can be some kind of spin groups, spin 4 or spin 6 and so on. It is sometimes you can gauge them, sometimes there is some global symmetry. For example, in the concept of standard model, you have the baryon number, lepton number, E1 symmetries which are basically accidental, but they are the global symmetries, okay. But you have also the gauge, hypercharge, weak symmetries and the color symmetries, but also you have a global non-compact symmetries because you have a space time, right? And that's how you define the spin. Without them, you cannot define the spins there. So you have a non-compact global symmetries, and fortunately the kind of theories we are talking about, we don't need to gauge them because we are the supergravity and all those things here, okay. So there is symmetry information we have. And now while doing that, we have to, the idea is to construct the higher mass dimensional operators. Now when you do that, you can construct as many operators as you want to, but there is some restriction because the construction has to be like they're independent operators. Now when I'm saying independent, what do you mean by the independent? So these operators individual, they are like a fields, they have some equation of motions, okay. So now once you construct multiple operators, let's say at some dimension 6, okay, you write down 1000 operators, okay, but not all of them are independent because you have the equation of motion up to dimension 4 Lagrangian for fermion, for scalar field, for gauge field, right? And then once you use those equation of motion, then you'll find out that these two operators O1, O2 are basically exactly same, or they are differ by a total derivative, okay. So if they are exactly same, then you can understand that the equation of motion connecting two operators. So if two operators or multiple operators are connected by the equation of motion, I'll call them redundant. So if there are 5 operators which are connected each other by the equation of motion, I'll pick one of them, and that is the primary goal, to connect not only constant operators but non-redundant operators, because in Lagrangian you cannot write down same operator again and again in a different form, okay. Now why I'm stressing on the total derivative? Because the quantum field that we are actually constructing here, okay, there's no boundary, right? And if there's no boundary, there is no boundary conditions. If there's no boundary conditions, we are not worrying actually about the boundary operators. So now if there's no boundary operators, so the topological terms and boundary operators, we are actually relevant for this construction as of now. So if two operators related to each other by the total derivative, we just say we'll declare them to be same, okay. Now what are the integration by parts? Remember, the Lagrangian density content is the polynomial of the operator are actually there, right? But actually the game is basically with the action, and action is basically d4x. If you're working in a 3+1 dimension, it's a d4x Lagrangian density. So then there's a possibility you can use, because of the presence of derivatives, use the integration by parts and so on. Now if you do the integration by parts, then two differently looking operators may be brought into similar form up to a total derivative, or not even sometimes total derivative is not needed. Okay, that means basically these two operators are actually same. So when you construct the operators, you construct the operators order by order in a mass dimension. Okay, and then for example, let's say dimension 6 I'm talking about. At dimension 6, what are the operators there? Then I have to filter them out, saying that they are not related anymore by the integration by parts and the equation of motion, and then we'll find out, okay, if I rely on the baryon number, left number conservation, if I subtract the flavor, all those things, then I'll get 59 operators. Okay, and these 59 operators I can mathematically ensure that they are there irrespective of whatever be your UV theory. When you integrate them out, what are the operators you can generate, you cannot get beyond this 59. And that was the, if you remember that cartoon, there's a big pond I was talking about. That big pond is nothing but the 59 operators. Okay, and once you extend hard dimension, for example dimension 8 and so on, okay, so then of course you encompass more and more, but the game is basically the same. Yeah, any question? Okay. So let me give you some example of that. For example, when you talk about the fields now, as Jose also mentioned briefly, so let me revisit that part. What about the gauge field? Because when you construct the operators, okay, we have to be also remember the construction is a gauge invariant way. Because if you spoil the gauge invariant, then you are really in deep trouble. So if in the operators, the gauge fields do not appear on face. Okay, they are actually hidden within the covariant derivative or in the field tensor. Okay, and then among these only scalar, fermion, covariant derivative and the x mu, they are actually appearing in the operator. And in this construction, though this phi, psi and the x mu, they are actually treated as the quantum fields, but also will upgrade the status of the covariant derivative as a Spurion quantum field. Okay, because it is singlet, it doesn't transform the internal symmetry, but you have to remember they transform another space-time symmetry. Okay, as a bispinner. If you think about the SU2L cross SU2R, okay, they transform as a bispinner. Okay, and then the operator, the composite operator that you are going to construct, they are actually polynomial of these four fields, and then the mass dimension of the operator is related by this one. Okay, and it's better to construct this operator in the while basis because that's how decouple your SU2L and SU2R part, and because while constructing all these fields are treated to be massless, so there is no issue with that thing. So now if I, for example, if I have this, these are the quantum numbers under this space-time symmetry, and these are the quantum numbers under this standard model gauge symmetry, then we have to go step by step. For example, we'll ask the question, what are the polynomials or invariant terms which are basically in a singlet under the space-time symmetry? Okay, so those are basically called the scalar. Okay, so we have found out 5 to the power 5 is a scalar. Okay, fine, but again, when I declare this as a part of my Lagrangian, then I have to make sure that all these operators, all these terms are invariant under the individual symmetries. So, but if you look at the quantum number of this 5, then 5 to the power 5 is not E1 invariant. Okay, and also it may not be invariant of other quantum numbers. So, though it's a Lorentz scalar, it's a singlet under or invariant under the space-time symmetry, but not under the gauge symmetry you are introducing. So, this is not a gauge invariant operator. So, I'm not allowed to write that operator in my Lagrangian. Okay, so that's why I construct the operator, and you have to check that they are invariant under the individual space-time symmetry and the gauge symmetry, and if you have some global symmetry and so on. So yeah, so this is the like a standard model. All the quantum numbers are there. Sorry. Oh, I think while making a PDF, something is missing.
No, this is the question of this is how do you open the PDF is a question. Opening is the next part of it.
How do you open the PDF?
No, there is one, I mean, if it is open with Acrobat Reader, it doesn't show the steps. There is one special way of what you can use it to open.
Okay, let them fix. In the meantime, if you have a question.
Yeah.
Yes. 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 So I'll come back to this thing when I talk about the defined models and then overlapping thing. I'll discuss that thing. Yeah, definitely. Okay, it's not there, leave it.
No, no,
I
no,
mean,
no, no. It's okay. I mean, hold on for a second.
okay.
It will come.
Change the slide and
তুই slide change করে রাখতে পারবি? হ্যাঁ,
Yes, yes, you know, sir.
now.
Oh,
I mean, we learn from our mistakes.
yeah. So this is not a change of basis then, because it's significantly effective observables. Okay, so yeah, so now if you look into this standard model symmetries here, okay, now the spin, mass, dimensions and the quantum numbers are there. Now you see in the Lagrangian, when and the method I am talking about to construct the effective operators, let me remind you, this is not only for higher mass dimension, starting from any mass dimension operator, even the renormable operators you can construct in the same way. For example, in the UCAV sector you can introduce this operator, right? It has a mass dimension 4, and look at the SU3, SU2, E1 quantum number. So SU3, SU2 they are singlet, and E1 is total is 0. So of course this is allowed term because this is a chiral term. And now if you talk about the 4 fermions and look at this mass dimension 6 and look at their SU3 quantum number and E1 quantum number, so this is an allowed term. Okay, so this is actually you generalize this thing. Okay, but certainly one can understand that, okay, so it will be naive to say that by hand you can do all these things, because there are more complicated structures. Okay, and so it's a bit difficult, and so what we did actually, we introduced this for you guys. So there's a program called group invariant polynomial, so where you inform this program about the symmetries, okay, different kind of quantum numbers, okay, and you just tell them, and then it will give you the invariant polynomials. And not only for standard model, you extend the standard model by some any arbitrary particles, but only restriction is basically this works for space-time dimension 3+1, and I think that's enough for the time being for the being a particle physicist. Okay. Okay. Yeah. So yeah. So now, so this is another way to look into the bottom-up approach. So as I mentioned, this is a standard model Lagrangian. You look into this process, okay, and then you believe that this process is not sufficient, to explain all the data for this scattering. So what you do actually, you extend by adding these effective operators. Okay, you are not changing the symmetry, you are not changing the on-cell degrees of freedom, you are just adding them higher and higher mass dimension operator. And once you add them, then automatically along with this diagram, there's an additional diagram pops out here. And now this both the contributions should match with the experimental evidences what you have seen, and that will eventually constant this parameter. Now in this construction, while throwing this one, this lambda and the c, they are the unknown, right? So that's why the Wilson coefficient, the coefficients sitting in front of this operator are called the Wilson coefficients, and they are basically, I do not have any clue about the origin. I am just throwing like a free parameter the way we introduce the Yukawa couplings in the standard model. Okay, we do not know what is exactly origin of that, what is the value of that. By fitting we can perform, we get to know about them. So similarly you just throw them here. So that's what the summary of the bottom up approach, and that's what you do with the bottom up approach, and that far you can go. And these are the example of SMEP dimension 6 operators, and that I was talking about the 59 operators, and I think it will be revisited by Jose again later, so I will not spend much time just to display you what are the interesting structures of this kind of operators. Yeah. So now, like in quantum mechanics, as you know, that you can change your basis, because basis is not a fundamental thing, right? You can change your basis keeping your observable same. So the same game you can play here. For a given mass dimension, okay, you don't need to restrict yourself to particular basis of operators, because you have a power of IBP and equation of motion. You can go from one basis to another basis, and the choice of basis is sometimes driven mostly by the phenomenological reasons, because in some all the informations are hidden everywhere, but sometimes some of the informations are very explicit in some of the choice of basis. Okay, and that's why we generally choose depending on what kind of phenomenology we want to do different kind of basis. For example, one of the famous basis by the Warsaw group is the Warsaw one, and then the strongly interacting light Higgs is the SLH basis, and you can see that how they are related to each other by this nice equation of motion and so on. So you can go from one basis to another basis depending on your choice. Those kind of freedoms are and so on. So you can go from one basis to another basis depending on your choice. Those kind of freedoms are there. Okay, but before proceeding, you have any question on the bottom approach? No. Okay, so now let's talk about the other one, which is the top-down approach, which is effectively integrating out the heavy fields. Okay, now when you basically integrate out, what you do basically, you have a low energy theory, what I have already mentioned. Okay, you start a UV theory, and you at some scale you match them. And generally, the first scale that we talk about is the mass of the lightest heavy particle that you are integrating out. So that is the mass of the lightest heavy particle is basically the scale where you are performing the matching. Okay, and then once you perform the matching, then it's not guaranteed that all the operators of the effective Lagrangian will contain only independent operators. Okay, then you have to pass through them equation of motion, integration by parts, and so on, such that you can map that effective Lagrangian into a non-redundant basis of operators. Yes.
So, by equation of motion and identity, we can use field definition.
Field definition is the equivalent statement for the equation of motion up to dimension 6. Beyond dimension 6, there are something issues are there, but one can still tackle it by modifying the quantum equation of motion. Yeah. Yeah. Any other question? Okay. So one has to keep in mind that this two constant is not only true for the bottom up, but the top down also you have to keep in loop about those aspects here. Now, what is the funny story about the top down is that you start with the now UV theory, okay, and let's say you are looking at this process for a UV process, okay, and then there is some pure standard model process like this, and then pure new physics process which is involving only new physics particles. At a low energy, this is redundant for us. We are not interested. We are looking for the on cell state which are actually standard model particles. Now, when I'm integrating them out, that means I'm expanding the propagator in terms of local operators, then I'm getting this. Now, if you recall what I do this diagram for the bottom up approach, you start with the standard model and then you add this operator. But here you are generating this operator, and because you are generating this operator, there's some advantage of doing that, because now you know what is the source of the operator. So you know exactly what kind of UV theory can spits this kind of operator. And not only that, these Wilson coefficients will be function of the mass of the heavy propagator and the couplings. So they have now the origin. Okay, and this is basically a huge difference between the bottom up and the top down approach, because in the bottom up approach, if you add 10 operators, those 10 operators are originless, they are free parameter. So when you perform the fitting of some observers, as you know, you have to treat them as a free parameter. But if you are coming from the UV theory and you generate exactly the same 10 operators, but though they are now exactly same 10 operators, but they are actually function of 2 or 3 BSM parameters. So effectively, the degree of freedom is reduced. This kind of theoretical correlation among the effective operators and the Wilson coefficient, that is actually there for the top-down approach, but the bottom-up approach, that information is missed out. So that's why it is not suggestive to use or translate directly the bottom-up approach result for the top-down. They can be completely misleading. Okay, because yes.
The same operator can come from different UV.
Yes.
Then how one can distinguish which UV from UV?
Yes. So I'll come to that. Yeah.
So bottom approach classifies this cannot unless we consider all operators or possible dimensions.
No.
It cannot retract back any specific model, right?
No. So it's depending on what kind of it guided by choice of your observers. So once I fix my observers, I know exactly what set of operators I have to deal with. Because other operators are, I will call flat directions. They are not sensitive to my observers. Like in BSM, for example, EV analysis, when you do, you can have 10 parameters, but not all of them are sensitive to my data.
Isn't it they classify specific class of models, so these operators can come from this class of models? And
No, that's the classifications. That's the classification. I'll talk about later that thing. Yes. Yes. Any other question?
so in the top-down approach,
Yeah.
so when you have only the relevant operators which are suitable to the UV theory,
Yes.
so at that time, is that meaning that you are missing something like some other effects which are not within the model?
What do you mean by that?
Like the effects, the model is not.
No, you declare that as a UV theory. You believe that's the complete theory of nature. Okay. Or what you can do if you don't believe that, what you do, your UV theory, if it is an effective theory, let's say, then you add more higher operators on them.
I think he is asking the most difficult question. He is saying that whether effective theory can completely, whether it can completely replace your full new physics or UV completely.
No.
So
UV effective field theory, that's also effective.
Yeah.
It's better to deal with First you have to understand whether there is a new physics around or not, because once you understand the presence of the new physics, then you have to do the full theory analysis. Yes.
So, I mean, it was that kind of a question. Because, say for example, I mean, the dimension 5 operator, if you take, I mean, there are many new physics models that it can correspond.
Yeah.
But so, therefore, the effect of the dimension 5 operator cannot distinguish the possibilities of these three different patterns.
No, that's not possible. Yeah.
That's not.
Yeah. I mean, that's not the in fact purpose of the effective field theory at all.
Yeah, because
Yeah.
now we don't know.
Yeah.
Point is whether we can see.
Okay. So I'll take 2 minutes because you talk. Okay. Any other question? Okay.
I'm going to shut you off.
Okay. Okay. So now, what are the diagrammatic or pictorial way to look into this integrating out? So this tree level I have already mentioned. Okay. And so now you can have a one loop diagrams. So in the one loop you can have a different kind of topology. For example, you have a propagators which are actually only new physics. So all are basically heavy propagators. Okay. So you can shrink them to a single point, or you can have this kind of diagrams which also contribute to the effective operators. Okay. For example, you can shrink these two propagators, but certainly you cannot shrink the standard model. And these are very non-trivial diagrams because these actually contribute to both local and non-local contributions. But what we are interested in the local operators, so you have to really remove the non-local contributions. Okay. But I will not go much detail about all these things. Okay. And this is one of the program that we developed, that if you plug in basically some UV Lagrangian, okay, and then you start to integrate that out, okay, and then what you can generate basically the one loop effective action for tree level process. Up to one loop you can integrate out this using this program, and not only that, after generating those effective Lagrangian, you can just run them down to the electric scale. Okay, so that's what you can do with this thing, and this is the website where you can go much more detail about this. Okay, done. So what did you do?
Just you raise the button once more. Yeah, see that experience works.
No, but it gives me skip some slides.
No, it will be.
I know my slides. No. Why don't you come and check here instead of So all this will be part of the injury time, right? You know, in soccer you have an injury time. So yeah. Again, so you have a time to ask some questions. Because we are dealing with the irrelevant operators, so it doesn't matter if you ask me irrelevant questions also. Yeah.
So for the uncorrelated,
Yes.
so let's say we have some observer.
Mm-hmm.
Motivated from that observer, we are like going to the direction of the unit.
Yes.
So there may be different unit places.
Yes. Yes. Not only that, you have to do you have to take a policy of that. For example, if you believe on that thing, like I'll do that minimally. That means with the standard model, I will not extend the standard model by too many particles in a single shot. Can you explain by a minimal, interactions or the particles? So yeah, but still you can have multiple solutions for that.
Yeah, that is minimal. If we do minimally also, that there may be two theories.
Yes.
Two theories,
Yes.
And those are the as
Yeah.
minimal. You are the comfortable.
Yes.
Because of same minimal.
Yeah.
So then,
Yeah.
is there any preferable?
No, so generally what you do then, once you identify those two theories, okay, then you integrate that completely now. Then you generate complete set of operators. Okay, so it will not generate only one operator, it will generate more other operators, right? Then you see what are the non-overlapping set of operators and how to discriminate using them. That's the next challenge. So it's like a go and forth kind of analysis you have to do to break those kind of degeneracies. Yeah. Yeah, okay. Okay, thank you. But in this mode, will it change? Oh, great. Yeah. Okay. So this is the third one about the unfolding. But I cannot talk you in much detail, but give you the essence of that. So start with the observation data, okay, and then you construct the effective operators to, because there are relations you set up with the observables in terms of the effective operators, right? And then you try to fit them and try to understand what are the effective operators actually are relevant for this kind of analysis, and then you basically unfold to see what kind of UV models you generally have. And that's what you do. You start with basically anomalous behavior of the observables. You identify them, what are the relevant SMAP operators, okay, and then you unfold them in terms of Feynman diagrams, pictorial way, and the background you basically use the knowledge of the symmetry to identify the heavy field propagators, and you can land up with the multiple solutions. For example, if I have, let's say, this kind of operators phi square x x tilde, x is basically nothing but the field tensor, okay, and then you will find out that you need at least two different kind of heavy fermions which are vector like to get this operator if you unfold that, okay, and that will lead to CP conserving and CP violating both sector operators. And then once you use that knowledge, then on the other hand side you use the program that I suggested and you plug in this Lagrangian, and then you will find out exactly this operator you are generating. So that's the complementary way you can understand, okay. So how from an effective operator you unfold and get to know what are the minimal way you have to extend the standard model, and then once you extend the standard model, plug in that Lagrangian and generate all the operators and then perform all the fitting and all those things. So that's the go and forth kind of approach you have to do. Okay, so now I'll tell you what are the phenomenological way to look into this aspect. I believe Shankho and will talk about, and Suhaito also will talk about more about those things. So what we do generally, so different kind of experimental data we use, but more pinpointedly because they are the electric precision data which are very useful because they rightfully measured quantities. And we use the Higgs data. Specifically, we use the differential cross section just to get to know about the PT and all those things, their behavior. And then we estimate the deviation from the standard model, and we try to recast some structure in terms of the effective operators. And then we either find the depending on what kind of approach you want to do, you define the chi-square or in the Bayesian way, or some modern approach. But effectively, it boils down to the fact that how do you constrain them. So based on this, you can now classify different kind of BSM theories. So how you do that thing? For example, let's say I constructed, I thought of like a 15 different scenarios where the standard model is extended by one heavy scalar at a single point of time. And this is a minimal way you can do. So you choose some different color singlets object. You can see all are basically color singlet, and then you have a colored object which you generally know in the literature as a electroquarks and so on. And then what you do, you choose one model at a time, you integrate out that thing and then try to find out up to one loop, okay, what are the dimension 6 operators you are generating, and that's this. Okay. So what you find out that if you have these models, and then if the HH tells you that these operators dominantly generated at the one loop, okay, and that also to the heavy propagators only, and then the cross means this operator is not generated up to one loop, okay, beyond one loop we do not know, but up to one loop we are doing this thing. And now you can see the lot of operators are generated by the same set of models. So that tells you that though we as a model builder claim I have defined a new model, I have constructed a new model and put in archive, how defined is that? From the effective field theory sense of that, they are not much defined. It's like using a defined mask, you are playing the same game. Okay.
Joydik, what are there inputs in the exiting for the crosses? What is this?
Okay, so this T stands for this operator dominantly generated at the T level.
Okay.
HH, your heavy loops are contributing.
Those are HH.
Yeah. Very bad projector, Yeah. So no, yeah. So now, so this is like an optics lab, possibly most of you have visited. So what you have done, so you have a, let's say you have a fine screen you have invented, which can is sensitive to kind of a single frequency, and if you pass let's say white light, okay, which contains a different kind of frequencies, and then it will spread out the frequencies and it collect on that way. So this is a similar idea. So basically all these screens are nothing but my set of observers. Now what is my observers? Observers are nothing but my set of operators actually. So now what I do, I pass through these 15 models through this. Now depending on which operators they are generated, their sensitivity to this observable will be based on that thing, right? And then what we find out in the first time that okay, so this 2 doublet model, complex triplet and complex quadruplet, they are actually equally sensitive to this observable. That means if I rely on only this observable cannot discriminate these 3 different models, or these 3 models are actually on the degenerate spectrum. And similarly all these leptoquark. Okay, so then I extend my new set of data, which is Higgs signal strength, which contains certain more operators, and that then we will find out okay, so these are again affected by the same set of operators and equally good on that, so I cannot break the degeneracy. But interestingly, among these 6, now this S2 contains some operator which is actually sensitive to this one, but which is absent on other 5. Okay, so I am not talking about the realistically possible, I am just from what is the best we can do from a theoretical perspective. So this is the best what we can do theoretically, okay, and that's the break the degeneracy. And then you increase the precision in the electric precision data, use some different kind of observables, and that's how if you carry on the process, and then you can see how the degeneracy in the models can be brought down. So this is the theoretical sketch and what is the best achievable scenario one can have, okay, that if you have a different kind of minimum, and let's see, there is a minimal models. Now if you extend your models by multiple scalars, now you can understand they will be more and more degenerate because they will give you the similar kind of things. So among those 50,000 models, possibly almost 99% models are actually nearly degenerate. Okay, so that's why even if you have some kind of excess, it will be really difficult to pinpoint whose model actually win the race. Okay, so that's what kind of notion we get from the effective field theory. And this is what actually just one simple plot to highlight the bottom up approach by the versus the top down one. So this is the ellipse which is almost invisible, but I hope you can see this. So this bigger ellipse if you see, so when we have used some H2 and this complex triplet, complex doublet and the quadruplet models, okay, and we integrate them out, we get the 9 operators. Now if I use these 9 operators from a bottom up side, then we are treating them to be independent, right? And if you are treating them independent in this Wilson coefficient plane, we get to know about this is the allowed regime. But once we know that okay, there are some different UV theories are there and we integrate them out, we generate exactly those 9 operators. But now those 9 operators Wilson coefficients are theoretically connected to that, and instead of 9 operators independent, they are function of 3 model parameters. And because they are theoretically connected, so now you can see the allowed regime is basically this minuscule regime. So that's why in a bottom up approach you always get an overestimation because the number of operators you are adding more, okay, and in the top down way because they are theoretically connected, so degrees of freedom is much more lesser, it's a much more tighter constant you get. So certainly you cannot use this ellipse information to put bound on the UV theories, you have to perform their fitting in an independent way. Okay, so I am almost done. So there are some fistful of EFTs. So effective field theory connects physics of different length scales that we have seen, and it's a very effective tool, especially when the new physics is unknown. And the top down and the bottom up approach, these are 2 complementary one, and different UV theories can be brought into the same footing, which you call the SMEPT for the time being. And this is a platform where you can perform the comparative analysis between different kind of models to put some kind of bias to understand them better. Okay. And so far we have the real data, we have electric precision data and the Higgs observable, but you never know the theoretical constant, the non-observation from the child electron flare violations and neutrino physics data and all those things. If you put more and more data, maybe that will be more interesting way to look into that thing. And what I didn't talk about much about the, if you have a CP violation, that's very interesting. If you find out some non-standard CP violations, that will certainly be a game changer because that can help you to discriminate in a primary notion that okay, the standard one is extended by a heavy scalar or a heavy vector like kind of fermion, or there is some kind of axial anomaly also. And the precision calculations are more important, so you have to go either computing the dimension 6 in the higher loops, or you extend the dimension beyond dimension 6 like dimension 8 and all those things. Computation of the renormalization group equation for the effective operators are very useful because if the scale is higher, then the lambda is basically let's say few TeV, and then to the electric scale that running in the precision era could be very important, so we cannot be ignorant about that thing. And what are the effective field they talk about so far? and what will be discussed, I guess, is mostly in the T equal to 0, 0 temperature. But this is not all about the effective field theory. There are certain huge genre of effective field theory where you have a finite temperature. You switch on the finite temperature, and then that theory becomes more interesting, and it actually widens up the much more applications starting from QCD, low energy QCD, cosmology, and even the condensed matter physics. So I would stop here, and thank you for your attention.
Questions?
Yep.
So let's say we have two UV theories,
Yep.
and let's say we have two UV theories, and what we want that we want to distinguish between two, and let's say we have observables that lies in, let's say, two energy scale. Let's say one observable is measured in some experiment which is at E1, and another observable is at, let's say, E2. So so to do that, do we need to take the lambda which we take, that thing such that the two experiments are valid for this lambda, or let's say we do for one experiment at a time and then another experiment at another time?
Okay. So let me give an example that one. For example, let's say you extend the standard model by some two heavy particles. Okay, there are two EV theories. Okay, you integrate them out. You basically get the effective operators at their mass scales, and to start with, to make a comparison, you assume their mass scales are basically same. Okay, so that's the lambda, capital lambda. Okay, and then you generate the effective operators there. Okay, you run them down to the electric scale. So electric scale, you have the electric fission data, Higgs data, and all those things. You perform fitting on them. So basically now your Wilson coefficient plane is basically now much more squeezed. Okay, and then what you do, you just started but now you want to use the flavor data, let's say, at the low energy, at the bottom mass. Okay, and then what you do, you start integrating out the Higgs, heavy gauge bosons, top quark from the effective operator and so on. Okay, and then you get a low energy effective field theory at the MB scale. Okay, apart from the running and everything at the MB scale, and then you perform the refit those again. So that is the how one should do actually. Okay, because you cannot merge the scales. Yeah.
Hi. How to determine when to use top-down and bottom-up approach?
Sorry, how to?
How to determine when to use top-down or bottom-up approach?
Okay, so bottom-up approach is basically we give a much more gross idea. For example, you have no clue about the effective operators on all those things. So that's why you perform the bottom-up approach. You basically get a window of the Wilson coefficients. Okay, and then if you're interested in specific to declassify the models or make a comparative analysis between different kind of UV scenarios, okay, then you do the top-down, and then you perform the complementarity among them.
So as I told in the slide that there are different models
Yep.
and there are filters.
This one?
Yes. So what are those colors on the boxes?
Colors in the box. These are okay. This is just to tell you that these are singled out from other, because they are not overlapping with other models. So they have their own identity. That means these, once you integrate out this particle, okay, you generate the set of operators, and when you integrate out any of them, okay, you get a set of operators. When you make a comparison, this model will offer you something which is not in others.
Means a set of operators which is not in others.
Yes.
Other. Okay. So can we insert one more filter? So is it done at dimension 6? So can we improve that filter by including higher dimensions at dimension 8 operator? Which
Yeah, of course. That's the precision actually. That's the precision.
means
For example,
higher dimension
yeah,
improve the
yeah.
classification.
But you have to, when the observers are also on the same level. Yeah.
When suppose we have multiple heavy fields in the full theory, and the suppose the mass difference between the two new fields is, if it is large, then probably we will first integrate out the heavier particle and
Yes.
then we'll go down. And
Yeah.
But if they are nearly same masses and two different kinds of new heavy fields,
Yeah.
can you tell how do we integrate?
Yeah, so basically your lambda is the light, the lambda is the lightest heavy particle. So if you have a M1, M2, M1 greater than M2, okay, M2 is the lambda. Lightest heavy particle mass is my lambda. because that's otherwise I can go to energy regime. If I choose M1, okay, I can go to energy regime which is less than M1 but more than M2, right? So then I can create that particle on shell. Then my effective field theory will be invalidated. So just to make sure my effective field is validated, I should work in a regime which is far away from the lightest heavy particle mass. So any other mass, heavy particle mass, will be above that. So I am safely do the effective field theory analysis.
So if you are screening things,
Yeah.
so if I rearrange the order of the screen,
Final, yeah, they commute effective. The final result will commute. So it doesn't matter. Because set of operators, right? Linear is.
additional operator means additional observable.
Yeah. So anything you can design by your own.
I have one question.
Yeah.
Is there some prescription given that I want to see some particular phenomena, and given my basis, and I can build up the effective operators which are sensitive to that observables? Like from below side, I am taking standard model thing, and I want to see some in the some observables like in flavor violation in top sector. Is there some well established prescription how to make those these effective operators?
So you have to rely on what people have already computed. So people have put a lot of effort to compute the observables in terms of the effective operators. Okay. So if your observable belongs to that set, then you immediately know that this observable will belong, depend on which set of operators. If it is not in that set, then either you or some of your colleagues have to do that job. It's as simple as that. Right? Would you like to add something to that? Okay.
You'll give me a job.
Yeah. That's the homework, maybe, Anyway, there's an exam, so homework can work. Yeah.
This is the ninth question. Why we are constructed that SMEFT? Because we know all the degrees of freedom of the standard model.
Yes.
So why we constructed that?
Okay. Because we believe the standard model is not the complete theory. Okay. But we also do not know what kind of new physics could be there. So now using the SMEFT operators, once we include more and more effective operators, because they are supposedly capture the footprints of the UV theory. So to capture the footprints of some unknown physics, we are increasing the higher dimension operators. The higher dimension operators are actually supposed to contain the relic of the UV physics which you do not know. That's why you are constructing the SMEFT.
But SMED operator all are constructed using that standard model degrees of freedom.
Yes.
So there is no new physics or new physics field.
There is no new physics field on shell, but the information of the new physics is there off shell.
Oh, okay. So that is
Exactly.
That is
for example, let's in the muon decay, if you think about, okay, you integrate out the gauge boson, then you get the 4 Fermi operator.
Right.
But 4 Fermi operator captures the information because your GF actually inversely proportional to the mass square of the gauge boson, right?
Exactly.
So that's how the information is there.
Oh.
Okay.
Okay, any good thing has to come to an end.
Yes.
And so
And I am here till 13th. I'm leaving on 14th. So till that.
So you are free to bother him with your questions as you come across.
Yeah, till 6 p.m.
Yeah. So, huh? Yeah, he will buy them coffee. That's Jose's suggestion.
Oh, I thought they will buy me coffee. Okay. Yeah, never mind. Yeah.
Okay.
Sure.
But anyway, it's fascinating to have Joydeep and for his very energetic and enthusiastic lecture to contribute to this Gyan series. So let's thank him once more.
Thank you.
But there is a bit of formalities that we need to do. So we will honor him with a traditional gamusa.
So were you waiting for my talk?
Yeah. So
It goes
your
well,
talk had
and
to be
they will
finished.
give you, otherwise we will
Yeah,
dump you.
exactly. So unless you give a talk, we cannot give it. Yeah. So.
And knowing me for 20 years, he actually can't risk that. Okay. Thank you. Okay. Thank you.
Okay, so have a peaceful evening and come back fresh tomorrow. Thank you.